What's up, algebros and broettes? We're doing math on the internet, so don't adjust your TV sets. Let's get linear. Hey, today we're going to take a look at section 5.2. We're going to talk about the characteristic equation for linear algebra. Just a few ideas to start with. Some information we had before about the determinant of the matrix A. That'd be -1 to the power of r times the products of the pivots in the matrix U when we've reduced when A is invertible. Otherwise, the determinant is 0 when A is not invertible. But I think it's usually best just to calculate the determinant using a more organic means. And you know that when I'm doing my row reduction to find the pivots in a matrix, I really sometimes don't reduce all the way to a triangular form. And if I am reducing at all, then I'm not doing any row interchange, so I don't have to worry about the sign flipping. I'm also avoiding things like scaling and just working with row replacement as an operation because it preserves the determinant. So I usually just skip over that. However, the invertible matrix theorem lives on in each and every single one of us, and we have two more things to add to it. I know you thought it was over, but we got a couple of other things left to talk about. Let A be a square n by n matrix, then that matrix A is invertible if and only if, a couple of things to add, so we have everything else leading up to S in the alphabet, and we continue on with items S and T. We have matrix A is invertible if and only if the number 0 is not an eigenvalue of A, and the determinant of matrix A is non-zero. So in order for A to be invertible, we have to make sure the determinant is non-zero, and this also coincides with meaning that 0 is not an eigenvalue. We have some properties of determinants that I'm just going to sort of remind about. We have A is invertible if and only if the determinant of A is non-zero. The determinant of a product of matrices, that is A times B, the determinant of A times B, is the same as the determinant of A times the determinant of B. If I transpose a matrix, the determinant is preserved, so determinant of A transpose is the same as the determinant of A. If A is a triangular matrix, then the determinant of A is the product of the entries on the main diagonal of A, which we talked about at the end of our last lecture. And item E, which we sort of just mentioned, row replacement operations don't change the determinant. If I do a row interchange, every time I do that, the sign of the determinant switches. And scaling the rows will also scale the determinant by the same scalar factor. And then a big idea for our lecture today, a scalar lambda is an eigenvalue of an n by n matrix A. That should be if and only if. If and only if lambda satisfies the characteristic equation, determinant of A minus lambda I equals 0. So let's talk about where this comes from. So if we're talking about an eigenvalue eigenvector system, then we have A times vector V is equal to lambda times vector V for some non-trivial vector V. So we'll say for non-trivial vector V. Because if V is the 0 vector, then yeah, A times the 0 vector is the same as lambda times the 0 vector. Of course it's going to be true. But it's more fascinating, it's interesting to us when this happens for a non-trivial vector V. But what did we say from last time? We said, well, here I can subtract everything over and do A times V minus lambda times V equals 0, meaning the 0 vector. And that from here I can factor V out on the right, and that leaves me with A minus lambda. But this doesn't make sense. I can't do a matrix minus a scalar. The only way I can do this or make sense of it is if it's A minus my scalar times the identity matrix. So I need this identity matrix in there in order for this operation to actually mean something to us. But now we still want this to be true for a non-trivial vector V. So think of this as a homogeneous matrix equation. So we'd say to have a non-trivial solution to this homogeneous matrix equation, we need that the coefficient matrix A minus lambda I is not invertible. Because if this were an invertible matrix, I could, in theory, find its inverse, multiply both sides by its inverse, and then all of a sudden my solution V is uniquely the zero vector times A minus lambda I's inverse, which is the zero vector, which is only the trivial solution. So we think back to the invertible matrix theorem, right? We think about all the things that it said. I sneezed, but I'm still thinking about the invertible matrix theorem. Even through my sneezing, I'm still thinking about it. And we're saying, okay, if I wanted, so we think back to what it said, and if I'm going from the other direction, we'd say, if I'm only going to have the trivial solution, then the matrix that I'm working with has to reduce all the way to the identity so that I only have the trivial solution, which means I have all of my pivots, which means I'm invertible. I don't want any of that. No, no, no. I want none of that. I want that I have a free variable, that I have a non-trivial solution to the homogeneous matrix equation, so then my matrix better not be invertible, singular, right? Which means that its determinant better be 0. So, okay, so putting this all together, in order to have this non-trivial solution, we need that the matrix A minus lambda I is not invertible. So we force, because we want this to be the result, so we force the determinant of A minus lambda I to be equal to 0, making this matrix A minus lambda I non-invertible, giving us our non-trivial solutions, trying to coax them out, saying, hey, give me the non-trivial solutions. I'm going to get them. I'm going to make the determinant 0. That's going to do what I need it to do. So this is our sort of aha moment. This is what we're going to want to be working with. Okay, so this is how we're going to get what we need out of what we're working with. We force that determinant to be equal to 0, and we solve. And solve for lambda. This is how we find our eigenvalues. This is how we generate these things from just a matrix as the starting point. Now this first question, this first exercise, says find the characteristic polynomial and the real eigenvalues of this matrix. So I start off similar to how we did before. I take this matrix, 2, 7, 7, 2, and I want to subtract away. I don't know what my eigenvalues are, but imagine that I have eigenvalues lambda, so A minus lambda I. So I want to subtract away A minus lambda times the 2 by 2 identity. So minus, and then just think about scaling lambda into the 2 by 2 identity. Right, so I2 looks like 1, 0, 0, 1. If I multiply lambda into it, I get lambda on the main diagonal, Greek letter lambda, and zeros off that main diagonal. And that's how that computation is going to look. Now, I want to go ahead and do the subtraction, and we really probably don't need to show this step. You're going to get so used to doing this computation that you can just go right away and start subtracting lambda on the main diagonal, because I'm going to get 2 minus lambda, upper left, and then 7 minus 0 stays 7, and then 7 minus 0 in lower left stays 7, and then last entry 2 minus lambda gives me 2 minus lambda. So I usually just start by just subtracting on the main diagonal, subtracting lambda away, but you can show the steps leading up to that too. This is my matrix. This is A minus lambda I. Now I want to find the determinant of this matrix. So let's find the determinant of A minus lambda I. We know how to find the determinant of a 2 by 2 matrix. I multiply on the main diagonal. Think of this just as a matrix, right? That's 2 minus lambda times 2 minus lambda, and then subtract the product on the off diagonal, so minus 7 times 7, my multiplication dot. And then I want to force this, set it equal to 0. And then we expand it out. Let's get some foiling. Negative lambda times negative lambda gives me a positive lambda squared. Then I have negative 2 lambda and another negative 2 lambda for my outer and inner terms. And then I guess my first term, 2 times 2 gives me 4. And then minus 7 times 7 is 49. And I set this equal to 0, and let's clean it up. So lambda squared, negative 2 lambda minus 2 lambda is minus 4 lambda. Combine the constants, 4 minus 49 is negative 45. That's equal to 0. And then now I want to think about, so this is actually my characteristic polynomial on the left-hand side. Let's name these things. I'm not quite done with it. Now we want to factor this. But right here on the left, we have the characteristic polynomial. It's a polynomial on lambda. It's a quadratic in this case. But if I'm thinking about the entire thing, so if I were to consider this entire thing, meaning the polynomial equals 0, then that's referred to as the characteristic equation, since I have my characteristic polynomial set equal to 0. But we want to take this characteristic polynomial on the left-hand side here, and we want to try to factor it if we can. If I can't factor it, we have things like the quadratic formula, you know. But this looks very factorable. So I set up with my parentheses, my sets of binomials, lambda times lambda leading the way to give me lambda squared. And I'm looking for two numbers that multiply to a negative 45, but that add to a negative 4. So I can do this with sort of guess and check by inspection. So it looks like if I'm multiplying, I'm going to want something like 9 times 5, and that seems to maybe do the trick. So 9, 5, and we'll say which one. So I have to have opposite signs to get this negative 4, so it should be negative 9 plus 5 in the factors. Lambda minus 9 times lambda plus 5. And this is now a factored version of my characteristic polynomial. And I can use this now to solve for what my eigenvalues are. So this means either lambda minus 9 equals 0, or lambda plus 5 equals 0. And solving this, I get lambda equals 9, and lambda equals negative 5. And these are my eigenvalues. These are my real eigenvalues. And I like to give them nicknames: lambda sub 1, lambda sub 2. So those are my eigenvalues. And that's how we find them. Right? We force that determinant equal to 0. Hey, let's do it again. Let's do it again. So now, I know I'm going to be subtracting lambda times the identity. I think it's fine to just start by, we know how that's going to look aesthetically. I'm going to be subtracting lambda off the entries on the main diagonal. Those other entries, anywhere else I have other entries, they're going to be preserved. So I like to just start with this. This is my a minus lambda I. Now I want to find the determinant of this matrix. Yes, I do. I promise you that I do. And 2 by 2s aren't so bad. Multiply in that main diagonal, 5 minus lambda times 4 minus lambda, and then minus 3 times negative 4. And we set that equal to 0. And let's expand this out. Let me FOIL this. I like to start with the last term of FOIL. Negative lambda times negative lambda is going to give me a positive lambda squared. Then I have negative 4 lambda, and then negative 5 lambda, and then 4 times 5, or 5 times 4, gives me plus 20. And then here I have minus negative 12, so that's going to be plus 12 equals 0. I don't want to forget about this term over here. So I got everything. I can go ahead and combine my like terms on this. So we have lambda squared. Negative 4 lambda minus 5 lambda is negative 9 lambda. 20 plus 12 gives me plus 32 equals 0. Now, this is my characteristic polynomial on the left. The entire equation is my characteristic equation. And if we're all thinking the same thing, I'm thinking this doesn't look like it's going to factor. I can't think of any factors that work. So I want to use the quadratic formula. What is the quadratic formula? Well, remember, that's negative b plus or minus the square root of b squared minus 4 times a times c That's all divided by 2 times a. In this case, we're thinking about polynomial, and traditionally thinking about ax squared plus bx plus c equals 0. But here I have a polynomial on lambda instead of x, but I still go about this the same way. What is a? Well, my coefficient on lambda squared isn't really there, which means it's 1. A is 1. B, my coefficient on lambda is -9. And C is 32. And I just start dropping these values in. And let's see what I get. So negative b, negative 9 is going to give me 9 plus or minus the square root of -9 squared. And it's that number squared, so I like to put parentheses around it. Minus 4 times a is 1 times c is 32. And then all divided by 2 times a, which is 2 times 1. The nice thing about factoring is it's fast and relatively painless. However, it's a guess and check method, and sometimes we can't do it. With the quadratic formula, we have to remember it. So there's that first thing. It's like, well, if I don't remember it, then I'm kind of in a bad position to start. But otherwise, it is going to give me an answer, and it's going to be a very direct answer. Let's continue with this. That was my little segue, my little speech. 9 plus or minus the square root of -9 times -9 is 81, minus 4 times 1 is 4, but 4 times 32, I like to think of this like 4 times 30 is 120. 4 times 2 is 8, so that should be 128. And all divided by 2 times 1 is 2, but I notice an issue right here. So if I end up subtracting under that square root, this is the discriminant, then that's going to be negative. So here, we'll sort of mention, we'll say, uh-oh, negative under the radical, under the square root, sad face. I know this is no good. This means we have no real solutions, or this means we really have no real eigenvalues. Is there such a thing as complex eigenvalues? You bet there is. You bet there is. Can we work with them? Yeah, we definitely can. Let me know in the so this is actually material that we don't really cover anymore. It's a bit dense, but I think it's very rewarding too. Let me know in the comment section below if you want to talk about complex eigenvalues that come from real matrices, real valued matrices. We can still maybe talk about it, but for now, we're tabling that conversation. But let me know if there's interest. If we can get this video to, let's say, 50,000 likes, then we can talk about some complex eigenvalues, because I actually like the material a lot. But okay, so then the answer for this one is just no, right? I found the characteristic polynomial, but there are no real eigenvalues, unfortunately. But we continue our journey anyways, because we're not going to let one setback stop us. Find the characteristic polynomial and the real eigenvalues for this matrix here. Hey, let's do what we've been doing. Entries on the main diagonal, we subtract lambda from them. So that's 6, nah, 6 minus lambda now. 9 in the middle, nah, 9 minus lambda now. That 3 in the bottom lower right corner, 3 minus lambda now. All the other entries, though, that are not on the main diagonal, they stay exactly the same. So fill them back in, because they didn't even get so much as a haircut. And this is a minus lambda I. And let's find the determinant of this. Now, however you want to do your cofactor expansion is up to you. I really like this third column, so don't forget that checkerboard pattern. You know how to do cofactor expansions. If I go here to this third column here, so plus, minus, plus, when I bring this term out, it's going to kill off whatever's left, so I skip over it, minus, but when I bring this term out for the cofactor expansion, it's going to just render that term unneeded, negligible, and then plus, and this is what I'm going to work with. So I'm going to bring out this entry, 3 minus lambda. I'm not going to flip its sign. And I'm going to multiply by the determinant of the 2 by 2 matrix that I get when I remove that entry's row and columns. That leaves me with this sort of upper 2 by 2 that isn't split. That's 6 minus lambda, -2. and then -2, and then 9 minus lambda. And I can compute this the rest of the way. Don't forget, though, I want to force this determinant equal to 0. But here I have 3 minus lambda times, here when I do this 2 by 2 determinant, I'm going to keep it in brackets because all of this stuff has to sort of stay together. That's going to be 6 minus lambda times 9 minus lambda minus -2 times -2. And all this stuff should be equal to 0. But let's see what we get. 3 minus lambda, and then times, let's expand this out. Negative lambda times negative lambda is positive lambda squared. I get -9 lambda. I get -6 lambda. I get 6 times 9 is going to give me 54. And then minus -2 times -2 is positive 4. So minus positive 4. Still, I want it to be equal to 0. Let's combine like terms where we can. So 3 minus lambda. And here I have lambda squared. Minus 9 lambda minus 6 lambda is minus 15 lambda. 54 minus 4 is plus 50 for that constant term, equals 0. Now from here, if I want to expand this out further, I can get a really nice polynomial form of the characteristic polynomial. However, if I'm looking for the eigenvalues, I really think expanding this out doesn't make it easier to factor. Leaving this as it is and trying to factor more is actually key here. So I'll show the polynomial later, but let me finish factoring while the factoring is fresh. So I have 3 minus lambda already. I can see one of my eigenvalues, in fact. But then here, I want to try to factor this part. So I'll say, okay, lambda and lambda, two numbers that multiply to a positive 50 and add to a negative 15. Are you thinking what I'm thinking? No, because I'm thinking what I'm thinking. So you're not thinking what I'm thinking? No, because you're thinking I'm thinking what you're thinking. But I'm thinking 5 and 10. Negative, right? We'll do -5, -10. And yeah, that's going to multiply to a positive 50. Yeah, it's going to add to a negative 15 lambda. So we're good to go on this. And what's nice about this is that now I can actually pick out the eigenvalues. So 3 minus lambda could be 0, lambda minus 5 could be 0, and lambda minus 10 could be 0. It means lambda would be 3. If I just add lambda over, lambda is positive 3. If I add the 5 over, lambda is 5, and here lambda is 10. So these are my eigenvalues. When I like to nickname these lambda sub 1, lambda sub 2, lambda sub 3, like this. But these are my eigenvalues. Now, if you want to get a very nice version of the characteristic polynomial, you would want to go back to this stage here, and you would want to expand this out further. So if I aim to do that, we'll say let me do the negative lambda first. Negative lambda times lambda squared is negative lambda cubed. Negative lambda times negative 15 lambda is positive 15 lambda squared. And then negative lambda times negative 50 is negative 50 lambda. And then if I bring the 3 in, so 3 times lambda squared is 3 lambda squared. 3 times negative 15 is going to give me negative 45 lambda. And 3 times 50 is going to give me 150. And still want it equal to 0. But then now I can go ahead and collect like terms. So I'll say negative lambda cubed. We'll say 15 lambda squared plus 3 lambda squared is going to give me 18 lambda squared. We'll say negative 50 lambda minus 45 lambda is going to give me negative 95 lambda. And then plus 150 equals 0. And this is a really good representation of that characteristic polynomial because we see that it's this third degree polynomial on lambda, right? You can really see how it should look in polynomial form. That classic, what we expect out of a polynomial. But this isn't going to be better for finding the eigenvalues. And that's usually what we want out of the characteristic polynomial and the characteristic equation is to find the eigenvalues. So for that, I really recommend not doing this, but factoring further, because that gave me the eigenvalue. Because now I would have to factor this. And I can factor it with factoring by grouping, but that's not going to be fun, right? But is it doable? Yeah. Is it fun? Nah. So I like factoring more. Let's list the real eigenvalues repeated according to their multiplicities. Now here's where we can start talking about what we were talking about at the end of last lecture. Since I have a triangular matrix, here's my sort of pizza slice of zeros. And you know what? I like to think of the zeros as pepperonis, or if you prefer vegetarian pepperonis, that is fine with me. So my little pepperonis of my little zeros of pepperonis. Let me know what your favorite pizza place is in the comment section below. Let me know what your favorite type of pizza is. Let me know what your favorite pizza topping is. Let me know what you're dipping your crust in, or if you don't eat the crust, or if you don't dip the crust but you still eat it. Let me know. There's my little triangular, I get my pizza slice with my pepperonis. Pepperonis. If we remember our theorem from last time, we said that the eigenvalues of a triangular matrix are the entries on the main diagonal. So I can already tell you what they are. I'm looking at them when I look at the main diagonal. To give this a bit more justification, let's build the matrix. We'll say, okay, on the main diagonal, I'm subtracting lambda. All the other entries are going to stay preserved. And then we have what then? Filling them in, writing them over. You know what this is going to do. There it is. And if I find the determinant of this matrix, remember the determinant of a diagonal matrix is the product of the entries on the main diagonal, what we were saying. So this is my A minus lambda I. The determinant of this matrix, and I'm probably going to, skip over the steps, but the idea is I would do a cofactor expansion down this first column. And so I'm really just picking out 5 minus, well, let me show it, 5 minus lambda. And then I have the determinant of the 3 by 3 when I remove that entry's row and column. So it's this kind of lower 3 by 3. And then I would do that process again. I would go down this first column. Remember that checkerboard pattern resets. So I got 5 minus lambda, and then I'm going to have 2 minus lambda times the determinant of the 2 by 2 when I remove that entry's row and column. And I'm saying don't do this. I'm saying if you remember the theorem, please save the time. But in fact, the cofactor expansion, even though this is a 4 by 4, the cofactor expansion is fast because it's triangular. So 5 minus lambda times 2 minus lambda. So then what about the determinant of this 2 by 2 matrix? It's 3 minus lambda times 5 minus lambda, and then minus negative 2 times 0, which is 0. And remember, I want to set the determinant equal to 0 at some point. And this gives me 5 minus lambda times 2 minus lambda times 3 minus lambda times 5 minus lambda, and then equals 0. And I can pick out these eigenvalues one by one. We say, well, lambda then equals 5, lambda equals 2, lambda equals 3, and I get another lambda equals 5. But if I noticed at the beginning that I had a triangular matrix, I wouldn't go through work. I would say it's a triangular matrix, so then the entries on the main diagonal are my eigenvalues. So I would just rush to the answer, say it's 5, 2, 3, 5. I can see them there. But this is sort of the supporting work if I want to explore that. Now, I was asked to list these eigenvalues according to their multiplicities. There's a couple ways that you could do this, and I would be happy. I'm perfectly fine if you list them out like this. You could do lambda sub 1 is 5, lambda sub 2 is 2, lambda sub 3 is 3, and lambda sub 4 is 5. But if you notice that I have a repeated eigenvalue, and we wouldn't really go through the same work twice for that repeated eigenvalue, you could do this. You could say lambda equals 5 with multiplicity 2. Then we have lambda equals 2 and lambda equals 3, and these are both with multiplicity 1, that they only appear once, but that lambda equals 5 actually shows up twice over. So this is just another way you could list it. That's it. We're going to start using this information next time. I have a couple of ideas I want to end with, a theorem and then a nice conversation about similar matrices that's going to help us move into a topic on diagonalization and working with diagonal matrices and a bit of why we care about them. We have, if A and B are n by n matrices, then A is similar to B if there is an invertible matrix P such that P inverse times A times P is equal to the matrix B. Or if I were to solve this for A, we would say A equals PB/P inverse. If we write, instead of P inverse, if we write Q, then we have Q inverse times B times Q equals A, so that B is also similar to A. So if A is similar to B, then it follows that B is also similar to A, and we would simply refer to them as similar matrices. So we would simply say A and B are similar. Changing A into P inverse times A times P is called a similarity transformation. And a nice theorem here, and we're going to explore what this means in just a second before leaving. But our nice theorem is, why do I care if matrices are similar? So what? It's a cool thing to talk about, but why do I care if I got a matrix and then another matrix that is similar to that other matrix? I'm going to tell you why. If I have n by n matrices, A and B are similar, then they have the exact same characteristic polynomial, and therefore they have the exact same eigenvalues with the exact same multiplicities. So if I can show that two matrices are similar, they have the same eigenvalues. And that's going to be important when we talk about showing that a matrix is similar to a diagonal matrix, because that's going to make our life very, very easy. Let's talk about what we talked about with similar matrices, and then I'm going to get out of here, and you're going to get out of here too. So if A is similar to B, if A is similar to B, then we had this relation here, that B is equal to P inverse AP. And I'm going to write this starting with B. So B is equal to P inverse times A times P. Now, if I were to solve this for A, I would get some statement that's identical. But what we're saying is P and P inverse are just invertible matrices. So I'm going to make a bit of a substitution. I'm going to say, let's let Q be equal to P inverse. P inverse is just some matrix. It's an invertible. P is a matrix. P is an invertible matrix. P inverse exists. Instead of calling it P inverse, let's call that matrix by some other name. Let's call it Q. And then it follows that Q inverse is P inverse inverse, which is just P, if that makes sense. So Q is P inverse and Q inverse is P. I'm going to make these substitutions. So here, instead of P inverse, I'm going to have Q. I'm going to leave some room because I'm going to write in the yellow again. But then instead of P, I'm going to write Q inverse. And then let me get back to the yellow. So this is now Q times A times Q inverse equals B. Now I want to try to solve for A. Well, what can I do? So to start, let me just rewrite it. To start, I'm going to multiply by, since Q is invertible, I'm going to multiply by Q inverse on the left. It's got to be on the left for both sides. And what's nice here is that Q inverse times Q is the identity. So what am I left with? Well, on the left-hand side, I have Q inverse times B equals the identity times A times Q inverse. And the identity times A is just A. So here we'll say Q inverse times B is equal to, well, I don't want to, we'll say A. I'll erase it. I started writing the identity again. I wasn't trying to do that. Because the identity times A is just A times Q inverse. But what would I want to do next? Well, I got to get rid of that Q inverse on the right here. So to do that, we multiply on the right by q to both sides. It has to be on the right, has to be on the right. And over here, q inverse times q is the identity. Really nice multiplying q inverse times q, right? So then, here on the left, we have q inverse times b times q equals a times the identity. And a times the identity is just a. So I have a equals q inverse times b times q for some invertible matrix q. And now let me just write this same equation, not going to change anything, but I'm going to write this part of it first. So if b is equal to p inverse times a times p, then this implies that a is equal to q inverse times b times q. And notice how these are it looks like almost the same statement, right? But here I'm saying, well, if b is equal to p inverse times a times p, and that means that a is similar to b, then saying that a is equal to some invertible matrix is inverse times b times that matrix, that's a equals q inverse times b times q, this means b is similar to a. So if a is similar to b, then b is similar to a, and then we just celebrate by saying a and b are similar matrices. Why do we care? We care because they have the same characteristic polynomial, they have the same eigenvalues, including the multiplicities. And hey, that's a pretty big deal. Thank you so much for spending your time with me. No matter where you are and what you're doing, remember to always keep learning, keep dreaming, and to follow your heart. You know, we're going to be back at it with more math, more cats next time. Yeah, take care of yourself, and I will see you next time. Hey, next time.